Thanks.
Yeah.
Forward.
Good.
Everything is set.
Good, thanks.
Good morning. It's a pleasure and a privilege for me to invite Professor Vijay Krishna to deliver the first keynote talk in Wine 2017. It's really a pleasure and privilege for me because I'm a big fan of his fabulous book on auction theory, which is one of the 3 Bibles or Bhagavad Gitas that I always refer to whenever I'm in doubt. The other 2 books being the book by Maskell, Winston and Green, The Microeconomic Theory, and the classic textbook on game theory by Roger Myerson. Professor Vijay Krishna is a distinguished professor of economics at Penn State University, and he is widely acclaimed for many, many influential contributions in a wide variety of areas, auctions and mechanism design. He's worked on games with communication. He's worked on repeated games, learning in repeated games, and he has also worked on voting. I would not like to belabor any more on the accomplishments and achievements of Professor Vijay Krishna. It's a real honor for me to invite him to deliver the first keynote talk here. Let's invite him with a wide applause.
Thank you very much. A great honor to be here. And I'm going to talk about the general subject of communication and cooperation. And this represents a couple of papers with these Yu Awaya, who's at Rochester, and John Morgan for Berkeley. And not all together, but 1 or 2 of the papers are with Awaya, and one is with John Morgan. This talk has a subtext, and the subtext is the following. It is that I feel that this is an area where certainly we economists can learn a lot from computer scientists, because computer scientists know a lot about communication. And I'm hoping that by showing you a couple of models and problems in this area, I will maybe plant some seeds of interest in some of the young people here, and they'll start working on these things. So all of yesterday, I sat through all these talks by the 4 tutorials, and I was just stunned in admiration at the accomplishments of what Kira calls this community, I think. So of course the subject that, oh, by the way, I should tell you that my colleague Nima told me that it's mandatory to have some photographs in computer science talks. So we don't do that in economics, so I had to find some photographs. So of course the classic area that has, where computer scientists and economists have come together, is auctions and mechanism design. And as you can see, these are the 3 Nobel Prize winners from 2007. Leo Hurwitz on the left, and Eric Maskin, and Roger Myerson. And after that, there was this loosely defined area called market design, which involves, it certainly includes all the work on matching, and this is the 2012 Nobel Prize, I believe. And this is Al Roth and Lloyd Shapley. And recently, there's been a lot of interest in economics on a subject called information design. And what is information design? Information design is like a dual to mechanism design. So in a mechanism design problem, you assume that the players have some private information which you're trying to extract with a view to some social goal or some private goal. And the idea is to provide them the right incentives so that they'll tell you the truth. Information design is slightly different. There you're trying to control the information that the agents are getting. And in some sense, the game is fixed, but you're controlling the information. So in mechanism design, the information is fixed and you're designing the game. Information design, the game is fixed and you're designing the information. Roughly, that's what happens. But my goal is to try to tell you that maybe this is a further subject, and this is the subject of my talk, is this, that I hope that we can follow the craze and create a new subject here called communication design. So that'll be my goal. Okay. And what I'm going to do is to talk about two very different problems. One has to do with what are called very simple sender-receiver games, and I'll explain what that is if you don't know. And the other is looking at communication in the context of repeated games and what that does in the repeated context. And that's okay. So let me begin by telling you a little bit about sender-receiver games, and this is work with John Morgan that we wrote a few papers on this. So what's a sender-receiver game? A sender-receiver game is just a two-player game. There's a sender and a receiver, obviously. And just to fix ideas, think of a policymaker, and to fix ideas, think of, let's say, somebody at the Federal Reserve or the Reserve Bank of India who must choose what interest rate to set. That's the thing about. So the parameter y is going to be the interest rate. And the correct interest rate, you will see what that means in a second, depends on the estimate of how much inflation there will be, let's say. Right? So the unknown state is how much inflation there is. And there's an economist who has good information about inflation, and that's the situation. And the policymaker, Janet Yellen or whatever, does not know theta, except she's hired the economist, and the economist is going to tell her what the expected inflation rate is, and then okay. Now, interest in the problem comes from the fact that they have slightly different interests in this thing. So in this example, this is just an example. So the states are uniformly distributed, and what the policymaker would like to do is to match the state, is to choose the interest rate to, let's say, match the inflation rate. Let's just think about that. The economist, on the other hand, is what macro people would call an inflation hawk. So he's in favor of higher interest rates for any given interest rate. He prefers a higher action for the things. So the ideal action for the policymaker is to just choose theta, and for the expert to choose, expert would like the interest rates to be higher, let's say. And in this case, higher by a constant amount, which is this B. So this is the kind of situation, okay? But the problem is here that the person who has the knowledge is not the decision maker. That's the thing. So the expert is informed, but the power to make decisions is divorced from expertise here. That's the thing, and the interests are slightly different. So if you look at this picture, and these kinds of pictures you'll see a lot. So I'm going to put the theta, let's say the expected inflation rate here, and the proposed inflation rate, proposed interest rate on the y-axis. And the red dashed line is the ideal interest rate from the perspective of the decision maker, the policy maker. And as I said, the economist wants a slightly higher interest rate, and so his ideal line is here. And this quantity I'll refer to as the bias of the expert. So what can we say about this problem? So we're just going to look at a simple kind of game, and the game is going to be just a simple communication game. The expert learns what the expected inflation rate is, this theta parameter, and then he sends some message, which could be some advice. It could be a recommendation of some sort to the policymaker, and then the policymaker receives his recommendation and updates her view of what inflation is, what value of theta is, and with that posterior distribution, chooses the interest rate that maximizes her expected profits. That's the simple kind of situation to look at. So what do we know here? What can we say here? So first of all, it's very easy to see that because the interests are not perfectly aligned, there cannot be an equilibrium in which the expert fully reveals what he knows truthfully to the policymaker. And of course, the point is, suppose there were such a thing, an equilibrium, then of course what you see in equilibrium, what would be implemented in equilibrium would just be the red line, because if the policymaker knew theta precisely always, she would just choose y equal to theta. Okay. But then if that were the equilibrium, then the expert would have the incentive to exaggerate the value of theta to get her to take a higher action. So there cannot be, full revelation is impossible in this setting. Yeah, so even no matter how small b is, it tells you that. On the other hand, there's always an equilibrium in which no information is revealed. So this we refer to as a babbling equilibrium, and that's a situation in which the policymaker pays no attention to what the expert is saying, which is a common complaint of economists, that nobody listens to us, and just takes an action based on her prior knowledge, which is it's uniform. So, and given these quadratic preferences, the best thing to do is to choose half. And since nothing he says is given any attention by the policymaker, the expert is indifferent and can say anything he wants. So this is always an equilibrium where everything is ignored, all information is ignored. Okay. Yeah.
If the policymaker knows that the economist is doing this, she can easily subtract B and
So, I'm sorry?
the policymaker can subtract B from the economist's.
No, here the economist just, even if he knows that the true value is a half, he's just sending some message at random. Oh, in the other one. Yeah, no, absolutely, that was the whole point. Over there, that can't be an equilibrium, but in equilibrium, it would have to be then, if the policymaker knew the state precisely, in equilibrium, she would have to move around the 45-degree line, but then the expert would try to fool her by giving a higher this thing. That would violate the equilibrium. So there's no such. There cannot be. Yeah. You're right, but then there's further thinking and so on. So it cannot be. Yeah, absolutely right. Okay. So now that's fine. So full revelation is never in equilibrium. Babbling is always in equilibrium. But what you can show is that in this example, as long as B is not too large, and here this is the relevant parameter, there are always other equilibria in which the expert sends some information and hides other information. And what do these look like? So they look something like this. Okay. So in this example, I chose B equal to 1/10. And so this is an equilibrium in which what the expert is doing is saying, well, I think the inflation rate is between 0 and 3/10. Okay. Or I tell you that it's between 3/10 and 1. And that's the only information that's communicated. The only information that's communicated is of this partition of the state space. If the true state is here, I only tell you that I know it's between 0 and 3/10. If the true state is above 3/10, then that's all the information I give you. So I know the value precisely. I know it's 0.1 or I know it's 0.6, but that's not what I'm revealing to you. I'm only telling you it's either below 3/10 or above 3/10. And so this depicts an equilibrium of the game, because this, remember, is the ideal point for the expert. The expert always wants the biased decision, and with these nice symmetric quadratic preferences, this distance is the same as this distance, which means that the person at 3/10, that is, if the state were 3/10, then the expert would be just indifferent between saying it's below 3/10 and above 3/10. If he says below 3/10, he would get this action, and above 3/10, he would get this action. So this is like a threshold where at that state, the economist is just indifferent. That's clear, right? And so everybody to the left would strictly prefer to be here. Everybody to the right would strictly prefer to that outcome. So this is an equilibrium with partial revelation of information, but this is the situation.
So the y-axis is like 3/20ths is the bottom.
Here, yes, exactly. It's 3/20. Yes, everything's very simple in this, and that's whatever that is. 1 plus 3/10 divided by 2. Yeah. So this is an equilibrium, and it turns out that for this value of the bias, 1/10, there are only two equilibria. One is the babbling equilibrium, and this is the other one, and there are no more. It can be shown. So in general, there are, for small values of B, there's another equilibrium in which the state space is broken into 3 bits. And then if it's further lower, then there might be another one which is broken into 4 bits. Okay? But given how many times you're breaking it, there's a single equilibrium. That's a very nice feature of this model. So in general, all the equilibria are partitional in this sense. They partition into intervals. It's not that they're partitioned, but they're partitioning into intervals. They're finite in number. And interestingly enough, they can be Pareto ranked in this problem. Yeah. So in this problem, what happens is that the babbling equilibrium is the worst, obviously. No information is communicated, but it's worse for both. It's not as if one is good for one party and better for the other. Both prefer this equilibrium to the babbling equilibrium. And if there was one with 3, then they would prefer the one with 3 sets in the partition to the one with 2 sets. So there's no, when you're ranking equilibria, they all like the one where the most information is communicated. Okay. But nevertheless, you can see there's substantial information loss here because this guy actually knows the state precisely. It's anywhere between 0 and 1, it's a continuous variable. And actually only 2 actions are taken. The actual decision is not very responsive to the state. In the system, this guy knows the state precisely, but this conflict of interest actually prevents information from being used used fully in this problem. So this is the basic model, and this is what I'm describing to you is a model outlined by Crawford and Sobel in a paper. Notice here, these models are called cheap talk models because it doesn't cost anything to the expert to, quote, lie or hide information. There's no cost to that. And there's no way that the policymaker can even verify anything about about what the expert is saying. So the communication is costless and it's not verifiable. These are a class of cheap talk models. Okay. Recently, there's been a lot of work in economic theory on at least partially verifiable information and what happens in those situations. But in this model, it's not like that. Okay, good. Okay. So the question is this the best that we can do? In the sense that, yes, question? Sorry?
How specific are these results to the quadratic form of the utility function?
They're not. They're not. They just depend on some single crossing properties of the thing. They're not. This part is not. But this example, of course, I'm working for that. All these hold for in more general this thing. And the quadratic and also the distribution can be arbitrary. It's not. I'm assuming a uniform distribution, so we can compute it. Okay. So we could ask, well, is this the most? Is this the limit on the information that can be transmitted in this problem? That's okay. So one thing one could think about is to say, well, what if we had more extensive communication? And this is the part which I want to label communication design. So this is a very simple kind of protocol. There's a single message sent from the expert to the policymaker, and then the policymaker makes a decision. Can we do better? Okay. So one thing you might say is, well, what if we had him send 2 messages? Okay, so I don't know why, but let's think about that. But of course, we haven't said anything about anything on the constraint, and we haven't constrained the messages in any way. They're completely arbitrary. So what is this going to do? Nothing. If you're going to send 2 messages, nothing's going to happen. You could just send both of them together at the same time. So what's the point? This kind of 2 stages is not going to help. So of course, this 2-stage communication like this is not going to improve matters at all. We'll get the same answer. Okay. So the interesting thing that happens is, what if I introduce a random event in between, and this is like not like that, and these commonly observed random events, somehow economists like to call them sunspots. So this is like we both observe a random event, it's called sunspot, hence the sum there. And so now what I'm proposing is this new kind of protocol. So the expert gets to learn theta, then he sends a message, then some random event takes place, then there is another message, and then the policymaker takes an action. Is it clear what the new protocol is? We're just introducing it. We could be tossing a coin. That would be fine here, a biased coin. Okay. But the point is this, the outcome of the random event is observed by both parties in this thing. So I'm going to show that this is going to make a difference now. This will make a difference. So this makes no difference, but if you introduce this random event in between, it makes a difference. So let's look at that a little bit. So I'm going to construct an equilibrium in this game now. Okay. And how's that going to work? So what's going to happen is that in the first stage, so remember in the original protocol, well, there was only 1 message sent. The break occurred at 3/10. Remember, that was at 3/10, okay. So now we're going to construct a new equilibrium in this more elaborate game, not too much more elaborate, but just 2 stages, with this random event in between, where in the first stage, what the expert tells the policymaker is either that theta is below 2/10 or above 2/10. That's the first stage of the communication. And then so now imagine that suppose we look at the case in which the expert revealed, in fact, that the state were above 2/10. Okay, so it's either going to be below 2/10 or above. So let's look at this thing above 2/10. So look at this picture and neglect this part. And just look at the situation from 2/10 to the right, above 2/10. And now in this, which I'll loosely describe as a subgame, because this is what's happening here, there are 2 equilibria again. There's the babbling equilibrium conditional on the common knowledge that we are above 2/10, but there's also a partially revealing equilibrium, the green equilibrium here. And you can check that this looks like this is exactly 50-50 from here. And this is also an equilibrium. So the distance from here to here is the same as the distance here. So at 4/10, again as before, the expert is indifferent between saying it's between 2/10 and 4/10 or above. Yeah. It's coming. It's coming in a second. Yeah. Yes, it is. It is. Yeah. There are models where it's not known, but here it is known. I'm looking at the simple case. Okay. So I want to say there are 2 equilibria in the subgame, and what the randomization is going to do is going to tell us which one we're going to play. So we're going to randomize between these 2 equilibria. That's what's going to happen in the event that we are the state is above 4/10. Okay. And precisely, it turns out that if we randomize in this fashion, that we play the more revealing equilibrium with 5 nines and this equilibrium with 4 nines. So it's as if we toss a coin, it comes up heads with probability 5 nines, and if it turns up heads, then the expert further reveals whether the state is above, below 4/10 or above 4/10. Remember, we're already in the sub-game where he's told his first message is that the state is above 2/10, and now if this event takes place, then he further reveals whether it's below 4/10 or above 4/10. And if the complementary event happens, then he just says, then there's no further communication. And there's no further communication. So is that clear what's happening? In the first stage, he divides the interval between, he breaks the interval at 2/10, and if the state is in above 2/10, then a coin is tossed. As the coin is tossed, then depending on the toss of the coin, either more information is revealed or no more information is revealed. Is it clear? That's the protocol. Okay. And some little calculations show, I won't do those here, that this is actually better than the one-stage equilibrium that I described to you, where the break was at 3/10. So that was the most informative equilibrium in the one stage, when there was only one stage of communication. In this two-stage with this randomization, this actually is better for both. Remember, these are all Pareto ranking. These are better for both, and you can measure the information going through in different ways. It's always better. There's no real this thing here. In fact, in this example, you can show that for, I don't know why the square root of 8 appears, but it does appear. As long as the bias is not too high, there exists an equilibrium with two-stage communication and the randomness and the randomization that is better than any equilibrium with one-stage communication. Right? That's what you can show. So one interesting thing is that with one-stage communication, it was the case that if the bias was more than 1/4, that the only equilibrium was babbling. Okay. And 1 over square root of 8 is larger than 1/4, so there are biases where in the single stage, no information can be communicated, but with these multiple stages, you can get some information across. Is that's clear? So it's telling you that there's this gap there. So the point here is to show that how you design the communication really matters in the information that's going through. Perhaps this is not surprising for computer scientists, but in this example, this happens. Yes? Yeah, so here messages are costless. There's no, or the expert is already being paid, and he's sitting in the office next door, and there's no other cost. That's all. So we're neglecting all costs of communication. There's no cost of communication here. Okay, so you'll say, okay, that's sort of nice. Okay, fine. 2 stages are better than 1. Okay, what about 3 stages? Maybe we could take this and break this even further, or I don't know why 3. Why stop at 2 now? You've come so far. Go to 3, 4, 5, and maybe every time the thing gets get better and better and better and better. Okay, more and more information revealed. So here's the little surprising proposition. The surprising proposition is that this equilibrium, actually there's a little typo. You have to remove the square root here. This is for b less than 1/8 now. Okay. It's an equilibrium with 2-stage communication, the one we found just now, of that kind. And this is actually optimal. So in this example, this is it. You cannot do better than this. There is no communication protocol that you can dream up of, however creative you are, which will lead to more information being conveyed than is conveyed in this equilibrium. So this is the optimal equilibrium over all communication protocols. That's the content of that. Yes? And,
Does this include private randomness?
uh,
So this is public randomness is what is
yes, it does. It does. It won't matter here. It won't matter. Yeah, it does not matter. Yeah, all protocols. So you'll see a reason why this is true. Okay. So why is this true, and how would we even begin to show this something like this? And of course, in all these problems, as you know, yes, question.
So why not only considering the right side? That further asking refinement, not on the left side.
It's not possible to break any on the left side. The B is high enough that you cannot break that any further. See, if the bias, the size of the bias constrains what you can do and preserve all the incentives. So that it's not possible to do that for this problem. If the bias were lower, then you can construct a more elaborate equilibrium, and that's involved in this construction. So you can break at the left and the right, and then yeah, you can. But for these particular values of the parameter, it's not possible. Okay. So the reason for this is the following. Imagine that all the information was transmitted via what's called a mediator, and a mediator is just a family of probability distributions like this. And what it does is, so the expert reports some state to this machine, and what the machine does is conditional on the state. It at random sends a recommendation to the policymaker. So this is a machine like this. And so is that clear? What a machine is? I'm telling asking computer scientists if they know what a machine is. Yes, I think they know what a machine is. So this is a machine, and so there's so how does the mediator work? Well, the expert learns theta and reports some theta hat, and the mediator recommends some random action depending on with these probabilities, and the policymaker hears the recommendation, then updates his beliefs about what the state is, and of course you want all sorts of incentive compatibility. The expert should report truthfully, and the policymaker should follow the recommendation. That's the incentive compatibility for the mediator. And there's a revelation principle that goes with this. It says every equilibrium of any communication protocol can be implemented via a mediator. So if you wanted to find take any protocol you can write down, any number of stages, all sorts of randomization, you can always reduce it to this mediator, looking like this. And indeed, so this is exactly like the revelation principle in traditional mechanism design. The space of mechanism, we don't know what that is, but we know that we can always reduce this to these direct incentive compatible mechanisms, and then we can search over those, and this is a similar problem. Okay. And so the result that the kind of equilibrium I constructed with two-stage communication and randomization, the fact that it's optimal follows from the fact that the payoffs from two-stage communication, you can solve for the optimal mediator, and then you just see, and as far as I know, this is just a calculation. I don't know why this is true. A calculation shows that the payoffs from this two-stage communication, that equilibrium that I described, so you send a message, then you toss a coin, and then you send another message. Just look over these, find the kind of equilibrium I constructed, find the best equilibrium there, is in fact optimal because the payoffs from that equal those from the optimal mediator. But I want to say that I don't understand, I don't know why. I don't know why this is true. There's no reason why this should be true, why 3 is not better than 2 or 5 is not better than 3 and things like that. Question? Yeah.
So like for bigger biases, does more stages help?
So you mean above 1/8? Yes. Yes, they do. Yeah, they do. But we don't have any idea what the thing happens. Actually, for bigger biases, the kind of equilibria that I constructed don't work. You have to make them communication that takes place is not interval based. So I might tell you that in the first stage that either inflation is very low or very high, and or it's intermediate. So things like that. So those are more elaborate kinds of construction. But so I'm sticking to the thing. So I want to say this is a puzzling kind of result, unexpected. We don't know why 2 stages of communication is enough, but certainly 2 is always better than 1, always. 2 is better than 1 always, and when the bias is not too high, it's actually optimal. That's the result that one gets.
You have the nature of the communication, optimal communication.
No. Only when the bias is less than. Yes, so what is true is that for all biases, you can show that 2 stages is better than 1. And when the bias is less than 1/8, there should be no square root here, it's actually 2 is optimal. That's the result. But you can always improve on 1, and the improvement on 1 comes not with these, as I said, these non-interval kinds of equilibria, which you can construct. That's the thing. So we need some help in understanding this and as to why this happens. So Nobu Kiyotaki, who's a rather famous macroeconomist, explained this result saying, well, it's like a marriage. When your interests are not too far apart, you don't need to go to a counselor. You can just work it out yourself. A mediator is like a counselor, and you don't do that. Okay, so let me move on. So it's there's a way. So there's a beautiful construction by Aumann and Marshall which says that we can dispense with the randomizing device, and the randomizing device can also just come endogenously via communication. But I won't bore you with that. There's a way to do that. Okay. So we don't know the answers to these questions, and I'm hoping you can do something like that. Okay. So I want to talk about yes. So these results are for the uniform quadratic thing. The first structure of equilibria is known because you have to do an explicit computation. As I said, I can't do that in general. Yeah. So now I want to talk about a slightly different problem, which also has to do with communication design. Yes.
Are we considering all the messages fade and transparent?
I'm sorry.
All the messages which are fade and transparent, are we considering?
I didn't understand the word you said.
Like the messages which are fade and transparent to bias, export,
Are all messages sent? Is that what you're asking? Yes, you can make this equilibrium so all messages are sent. So you never have to worry about off equilibrium messages and things like that. You need some randomization, weak strategies. Yep.
When you say 2 stage is better over all other communication protocols, do you mean only when communication is in the form of partition or any sort?
Any.
Not just this part. Okay.
No. It's completely, because the mediated settlement, the mediated solution is completely general.
Okay.
It includes everything, so we don't have to. Okay, so I'm going to talk very quickly about a second kind of result in the context of repeated games. And so here the idea is, so you know that in economics we just use repeated games as a way to think about repeated interactions as a way to think about cooperation and collusion in particular, and this is the sort of motivation. And we want to formalize this idea that somehow communication is necessary for cooperation or collusion, if you will. So whether cooperation is good or bad it depends on the context. So we want to formalize the idea, or at least identify some circumstances in which without communication you cannot cooperate, but with communication you can. We're trying to formalize this idea. And this is important for practical purposes, because in antitrust law in most countries, and definitely in the United States, there is a distinction between what's called tacit collusion and explicit collusion. So what's the difference? So suppose there are 2 airlines and you're looking at their pricing on certain parts, and what you see is Whenever one airline raises its price, the other airline raises its price, and then you go on for a little while, and then there's a little price war, maybe for a little while, and then again, when one raises, the other raises. So you go to the court and say, look, these people are colluding. It looks like they're colluding. Their prices are moving together. The courts will throw that out. They won't accept this. So in fact, this ruling from the Supreme Court says that tacit collusion is not in itself unlawful. Okay. What is unlawful is talking about it. If I call you up and say, hey, raise the price tomorrow, I'm raising mine, then that's unlawful. Actually, it's not just illegal, it's criminal. And you can go to jail for that. The manager who does that will go to jail. So in the law, there's this distinction between tacit collusion, explicit collusion, and part of what we're trying to do is to give some theoretical basis for this distinction. So if you think this is, I'm just talking out of my hat, here's some data which tells you. So what happened was in the 1990s, in the early 2000s, there was lots of these cartels were busted, mainly in Europe. So the European Commission on Competition aggressively prosecuted these cartels, and as part of the deals that they made was that they would reveal the inner workings of the cartel. And you can go on the European Commission website and read all these reports. And what amazing fact is, so these are all industries where there were cartels. I've just given you there were like 21 cases, but here I've just given you a sample of these. So they were asked to say, how did you function? How did you manage all this? And they said, oh, well, all of us flew to Zurich. Nothing takes place in Europe. They all go to the rest of it. They go to Zurich. We all flew to Zurich, and we met in this hotel, and we talked about things. And these are cartels which functioned for at least a decade, each of these, before they were busted. Sometimes 20 years. The amazing thing is how often they went to Zurich. Yes? These guys are going every 2 to the week. They're monthly, 1 to 2 months, monthly, quarter. They're regular meetings in Zurich to keep the cartel going. Right? So this is exchange of information of some sort. We don't know what they talked about. And so what is the information that they talk about? It's not about costs. They don't change that much. Okay? What they talk about always is how much I sold, how much you sold, how much you sold. They don't even talk about prices. Okay? So all the information that's exchanged is I sold so much, I signed a contract to supply so much citric acid last week, and you supply the contract. All the information that's exchanged is about sales. This is just a fact I'm telling you. This was discovered in these cases. So I'm going to try to explain that in a second. Yes. Well, the reason is they have explicit or implicit market share agreements, right? So they know that we've sort of come to an agreement that, because of my size, I'm going to get 30% of the share, and you're going to get 20%, and he's going to get 10, and something like that. And this sales information, they keep track whether my market share is roughly what it's supposed to be. That's the reason. So I don't care what price you are charging. You're undercutting the price. I don't care as long as you don't sell too much. I'm happy. That's so they're quite clever about this. Yeah. No.
Seems like something that I could look up online in some sense, like a company could just post it.
No, not weekly. So those comes with a lot of delay. When they write their quarterly reports, that's why they meet every weekly and things like that to do that. That comes with a lot of delay and has to be verified.
I guess it was not just also this agreement, right?
Yes, but we don't know how. Yeah, absolutely. Yeah, but the law does not make a distinction between private and public. All communication is illegal. The exchange of sales information is explicitly forbidden in the United States. What is not forbidden, and which many companies use, is the publication of aggregate information. So what they do is each company reports to the Ball Bearing Trade Association, and then the Ball Bearing Trade Association says industry sales in the last quarter were so much. That's also helpful because then you can compute your market share because you know the denominator, Prof. Leach, right? That's from the, yes, question?
What makes them say truthfully?
I'm sorry?
What makes them tell the things truthfully? Like, how do you know it's true?
It's coming. It's coming. That's the whole point. That's the whole point. Yes, that's the whole point. Absolutely. Very good question. It's as if I had paid you to ask that question. Okay. So I'm going to, given that I only have 15, 20 minutes or something, I'm going to try to give you the main idea through 3 examples. And if you understand the examples, you'll understand the main idea. And this is not an elaborate model. This is just the familiar prisoner's dilemma here. Okay, so there's a prisoner's dilemma here. And in undergrad, you can figure out that if you were to play this an infinite number of times and there was some discount factor, delta here, this delta is the discount factor. By the way, microeconomists always use delta and macroeconomists use beta. They could tell the difference between the 2 professions always. I noticed somebody yesterday used the beta. I was unhappy about that. But that's okay. But so with what's called perfect monitoring. So what is perfect monitoring? Perfect monitoring is that we play cooperate or defect, and then I see perfectly what you did last period, and then we play again. I see perfectly what you did, you see what I did, and we play again like that. So that's when I can perfectly monitor everything that's happening in the past. It's very easy to see that provided delta is more than 1/3, we can cooperate forever, right? And the thing is very simple. We start by playing cooperate. Both of us cooperate. If anybody defects, then we defect forever, and we're done. Yeah? Okay. So that's not that interesting. So I want to look at a slightly different situation, which is more realistic, which is what I'm going to call imperfect monitoring, but imperfect monitoring of a particular sort. So what's going to happen now is that we're going to choose our actions, cooperate or defect, but I won't see what you did. Okay? What I get is a noisy signal of what happened last period. And the noisy signals in this example are the following. I only get to know, I get a signal which is high or low, and you get a signal which is high or low. And this is the joint distribution over signals. Okay? So what this arrow is depicting is, I'm looking at a particular structure. I've rigged it right now in the example, that if both of us cooperated, then our signals will be perfectly correlated. With probability half, we'll both see a high signal, and probably half will both see a low signal. Okay? On any of the other cells here, the signals will be completely independent. Okay, so they'll be independently distributed with 50-50 in this. So this is the joint distribution of signals, which results if the play in the previous period is in one of the red cells, and this is the joint distribution that results if it's in the blue cell. But this is the only thing you see. So you might be worried about payoffs, but let's put that question aside for a little while. We'll come back and take care of that problem also in a while. Okay. So the only thing you see are these private signals in this case. Okay. Just to fix ideas, it's not a perfect model. Think of this as the cartel charging a high price and a low price. That's the decision I'm making. And then what happens is that results in some sales, and these are my sales that I'm observing. Just think of that if it helps you. So my claim is that with this monitoring, this kind of monitoring, this is what I'll refer to as a monitoring structure. With this kind of monitoring, it's impossible to cooperate. No matter how patient you are, remember, with perfect monitoring, provided delta was more than 1/3, you could cooperate. Here, no matter what the value of delta, no matter what the interest rate, this is the only equilibrium path. So why is that? The reason is this monitoring, this structure has the following property, that the marginal distribution on the other person's signals is 50-50 here, and it's 50-50 here. Is that correct? Yes? Just a fact, right? The marginal distribution is the same. And what this means is, suppose instead of cooperating, I just defected forever, okay, this would not provoke any response from you, because you would still see heads half the time and tails half the high half the time and low half the time. And whatever strategy you're playing, it can only be conditioned on the signals you've seen. So I haven't changed the distribution of what you're doing, and so that means that I can effectively cheat in the short run and never be punished. So that means that this is the only equilibrium path. Okay. So this monitoring is so bad that cooperation is impossible in this problem. Okay. But now I'm going to add communication to this. So this is the flying to Zurich part of the thing. So now what we're going to do, we're going to play, then the signals will be realized, then we fly to Zurich, and we tell each other what the signals are. But this is cheap talk. I could lie if I wanted to. I could say my signal was low when it was high. I could randomize. I could do all sorts of things. Okay. So now my claim is that with this cheap talk, which is added on, now it is possible to cooperate. So remember, without cheap talk, cooperation was not possible. But with cheap talk of this sort, it is possible. Interesting. And here is provided delta is more than a half. Okay. So what is the equilibrium strategy? The equilibrium strategy is we're going to cooperate, and then I'm going to report my signal truthfully to you, and you're going to report your signal truthfully. And the future play will be dictated by what we say in Zurich. Right? So if our reports match, right, if we both said high or both said low, then the next period will cooperate again. And if it so happened that I said high and you said low, then there'll be no future cooperation. Is that clear? That's the strategy. Okay. So now let's see why this is an equilibrium and why you want to tell the truth, etc. Right? Okay. So why is this an equilibrium? So first, suppose I have not defected. So we both played cooperate. You're supposed to cooperate forever. Suppose we started like this, and no bad event has happened. Our reports have always matched until now. And now, suppose I have not defected. Do I want to tell the truth? That was the question. Do I want to tell the truth? So of course the answer is no, because if I haven't defected, if I get the signal high, I know for a fact that you also got the signal high. How could it benefit me to say low when I know you got the signal high? Because then that would mean they would start defecting forever. Our reports wouldn't match, right? And I have no incentive to do that. Is that correct? So if I have not defected, then I don't want to lie. And now it's a very easy calculation to see that actually I don't want to defect, right? Because along this path, I'm getting an average payoff of 2. If I undertake a defection of 3, I'll throw us into this thing. Then I won't be able to predict what your signal was, right? Because if I get high, there's only a 50% chance that we match. And no matter how hard I try to lie and get around it, I won't be able to predict where your signal is. So with probability 0.5, you'll be thrown into this punishment. Is this clear? Yeah? Okay. So the fact that once you defect, things become independent, this means I'm unable to predict what your signal is. So when we meet, you'll be telling the truth, but I'll only be able to match you with probability 0.5. And that's good enough to prevent me from defecting. So with cheap talk, with adding this communication, we can cooperate in a situation where the monitoring was so bad that if we didn't fly to Zurich, we would not be able to cooperate. That's clear what the message is here? So how much time do I have? Who's keeping track? 5 minutes, okay, good. So I'll really move along. Okay. So I'm going to skip all this and come to just outline the model, tell you the main result. Okay, so in general, this is going to be some n-player game. There's some actions we take. There's some signals that we get. And I want you to now precisely think of this. These are the prices we are choosing. And then these are my sales. The signal that I'm getting are my sales. And the actions of all the players determine the signals in this stochastic way. So given the actions, there's a probability distribution over the joint signals. And then my payoffs, of course, depend only on my price and my sales. Right? So I just multiply the two together and get my revenue and subtract off the cost. So I know my profits just like that. Okay? And then what I could compute from here is the ex-ante payoffs, that is, if this were the joint action, what would my expected payoffs be? Well, they would be my ex-post payoffs weighted by the probabilities of getting this, and Qi is just the marginal distribution of Q on my signals alone. So I would compute the expected payoff. So before I take my action, I am, this is the relevant calculation. I'm observing my payoffs because, in fact, the signals and my action, these are all the things I know, completely determine my payoff. So there's no contradiction here. And I'm going to compare this to, so this is the kind of picture I have in mind. So this is the set of feasible payoffs, which is just the convex hull of the payoffs from each cell. There's some one-shot Nash equilibrium, mixed or pure, and I'm interested in knowing when can I get to the efficient frontier here. That's the cooperative kind of solution that I'm thinking of. So in the repeated game, what happens is I choose an action, then these signals are realized, then I observe my private signals, and my strategy just is a function only of my private history. My private history is just all the prices I have charged and all the history of my sales, and I decide what I'm going to do today. So that's fine. When there's communication, we have all this. We can exchange cheap talk messages. Now I know everything I knew before, but I also know the results of all the past meetings of what was said in the meetings. I could conceivably condition on that. And this is the main result. And at the moment, it seems horrible because I haven't told you what these conditions are. So it says to fix a large delta. Delta has to be large enough. If it's close to 0, there's no hope of proving this result. So there's certain conditions on the monitoring such that with communication, there's a nearly efficient or cooperative outcome that can be sustained, whereas all equilibria without communication are bounded away from this efficiency frontier. And there are 2 steps to showing this. This is the hard part. The hard part is saying that if you couldn't talk, what can we say about the set of equilibria? And these games are called games with private monitoring, and there's no known algorithm or anything for computing what the set of equilibria are. So that's the first step, and then the next thing is just a construction. We construct a nearly efficient equilibrium here. And so I won't, in the interest of time, I won't tell you. But one result is the following. I wanted to show you this because it's something I learned from computer scientists. So the first result is if there's no communication, then all Nash equilibria of the game with this discount factor, and this is the monitoring structure. Remember, this is the family of probability distributions. We tell you how the signals come about. Is completely contained in the epsilon coarse correlated equilibria of the one-shot game. So this is just the one-shot game. So you want to know what happens in the repeated game, that's a complicated object. But you can say it's completely contained in this. And the value of epsilon, we can give a precise formula for, is here. So this is just the same discount factor. And this is the only new thing that's appeared. This is just a normalization of the payoffs. This is the only new thing that's appeared. And what this is really, it measures how easy it is for other people to detect that I have deviated effectively. Yeah? So this is a distance between 2 distributions. One distribution here and one when I play something different. And I'm measuring how far do these distributions move. Right? So if they hardly move, then it's going to take you 10,000 years to figure out that I've actually cheated. But if the supports are different, then you know immediately. If they overlap a little bit, then it'll take you faster. So this is a measure of that. And this formula tells you exactly what this thing is. And this idea of a coarse correlated equilibrium, it's like a correlated equilibrium, but everything is ex ante. I first learned about it. I didn't know about it. We were working on something similar. And then I got Tim Roughgarden's book, 20 lectures on things. I was just flipping through it, and I saw this definition. I said, wow, that's exactly what we need. And that was the result. And so, of course, this is a more permissive notion than correlated equilibrium. So time is short, so I will just show you So then we construct, so that tells you what the bound is, and then we show how you construct an equilibrium communication. Yes?
So just to get some intuition about the statement of the theorem,
Yeah.
it seems a bit unintuitive to me given the examples. So my intuition is that the first example you gave is more robust than the second, in the sense that, you know, if every player, like my own marginal distribution over signals was different under corporate, and the other strategies,
Yes.
then for large enough delta, right, I would be able to, we would have like an efficient
Correct.
equilibrium.
Correct.
So in the statement of the theorem, I'm not sure what the quantifiers are. So here, right, so the intuition is for most games of that form,
Yes.
we would have an efficient equilibrium.
Yeah.
Whereas the statement is sort of, it's not clear what the quantifier is on the structure of the game.
Quantifiers are the following. First, I'm going to find a delta bar, and then I'm going to fix any delta above that number. And now it's not going to change. And now I'm only going to change the monitoring structure. So that's the order of the quantifier. So it doesn't contradict what you're thinking about. So in the examples, I just want to say, in the examples, eta is 0. In the examples, eta is 0 because those marginal distribution didn't move at all. And this is just measuring how much the marginal distribution of the other players. And so in the examples, the Nash equilibria are exactly equal to the coarse Corley equilibria. In the prisoner's dilemma, that's just the defect effect point. So that's why I'm moving too far away. So I want to say we know what happens without communication. We know this bound, and then it's a construction of what happens when we can fly to Zurich and talk. And the structure of the equilibrium is similar to what was in the example, except it's not completely straightforward. So what happens is we start playing the cooperative outcome, and then we report our signals. I've denoted these X, Y, just because they're schematically, they're just two players. And then we have to move probabilistically in the two directions. So with some probability as a function of the reports, we'll start punishing, and with some probability as a function of the reports, we'll come back to this good state. So in the example, this was 1 and 0 if there was a match or there wasn't a match, but in general, you have to make a probabilistic thing. And lying under this problem, inside this problem is a mechanism design problem. How do I give people the proper incentives to tell the truth, which is the question you made? And we exhibit explicitly a rule which determines those probabilities so that everybody wants to report truthfully along the way. And then this is the formal statement of the lemma. Another feature of the example was that along the path, that is when you were cooperating, signals were highly correlated, and when somebody defected, they became less correlated. In that example, they became independent. And this second parameter, gamma, is measuring that effect. And so this is the formal statement of the theorem. And in a more elaborate signal structure, this is what happens. This is again the prisoner's dilemma. The highest payoff you can get without communication is 0.77, but with communication you can get up to this for those parameter values. This is exhibiting how the theorem works in this thing. So here also, you have to design the communication protocol within the cartel, so to speak, so that everybody has the incentive to report their sales truthfully, and the cartel can sustain high profits. So here we make use of the fact that we in fact assume for the second part that the signals are affiliated. You need to say something about the correlation structure of the signals, just arbitrary. We have an example to show that you cannot dispense with this assumption completely. That if, so for instance, the second example I didn't talk about there, it was the mirror image of the first example, where if you cooperated, things were independent, and when you defected, they became perfectly correlated, and then you can show in that context, communication cannot help you. It does not help you. This is a question I think that only computer scientists can help us. Because in this construction, all the communication is public. That is, every member of the cartel, we're in the same hotel room and we're talking about what's happening, and right? This is all communication was public. And you asked about private communication. The other thing, here I don't know the answer. It may be that private communication is even better. That is where 3 players, then maybe 1 and 2 exchanging messages, and 2 and 3 exchanging messages, and maybe some public communication. There could be other protocols which could be much better, and we don't know the answer to that. So I'm going to stop here. Thanks.
So in the interest of time, we'll take the questions offline.
Good.
But let's thank Professor Vijay Krishna for an excellent talk and a very excellent, thought-provoking talk. I must also thank Professor Arunava Sen from ISI Delhi. He was the one who put us in touch with Professor Vijay Krishna, and what a lovely talk it has been. Thank you again.
Thank you.
Yeah. So over to Umang Bhaskar, the chair for the next session. Please come. You'll have to clap one more, a loving gift.
You can fix it to the back pocket. Just turn this around.
Yeah.
Should I give you?
Yes.